So now we're going to talk about enzyme kinetics, and we're going to talk about how we can experimentally determine the kinetic properties of enzymes. So remember that when we talk about reaction velocity, what we're really just talking about is the change in either the amount of product over time or substrate. And so usually experimentally, it's easier to measure the change in product concentration. You can use an enzyme that produces a product that you can detect somehow. Either it produces a colored product or it somehow changes the optical properties that you can directly measure. And then you just measure that value over time, and you can determine the velocity of the reaction. The only problem is that the velocity changes with substrate concentration. So here you can see different amounts of product being produced given different amounts of substrate. So if you start with a small amount of substrate like this, then the product formation rate is very slow, and then as you increase substrate concentration, you see the rate go up. But over time, the amount of product produced per second goes down, because as you use up the substrate, there's less substrate available, and so the reaction slows down. So instead of describing the activity of an enzyme in terms of just velocity, we use the initial velocity. That's just the velocity of the reaction at the beginning of the reaction, when the substrate concentration should be much higher than the product. In fact, in the very beginning, if you're doing this experimentally, you usually start with zero product available, and then the substrate concentration goes down over time. But again, in the first few seconds or minutes, the substrate concentration should be appreciably much higher than the product concentration, also usually higher than the enzyme concentration. But the point is that during those first few seconds or minutes, the reaction velocity, the change in product concentration over time, should be more or less linear. And so that's what these dotted lines represent. So each of these is the initial velocity for these different substrate concentrations. So this is the initial velocity when the substrate concentration is 1 micromolar. Here's the initial velocity when the substrate concentration is 0.5 micromolar. And down here, this is the initial velocity when the substrate, this is the initial velocity when the substrate concentration is all the way down at 0.2 micromolar. And so we can show then it's convenient to graph the initial velocity versus the initial substrate concentration. And usually you get a graph that looks like this, kind of a hyperbolic graph where the initial velocity increases or is low when substrate concentration is low, but it goes up very quickly as substrate concentration goes up. And eventually it reaches a plateau. So there's a point at which the initial velocity or the increase in initial velocity becomes smaller and smaller as you add more and more substrate, and we call that point the V max. So eventually this line, if we kept increasing substrate concentration, would reach V max, and that's usually the point at which the enzyme becomes saturated. So what that means is there's so much substrate available that all of the enzyme active sites become bound up. So that means there's no more way to increase the velocity, because there are no more free enzyme for the substrate to bind to. And so the reaction rate then, that initial velocity, is dependent on the substrate concentration when substrate concentration is low. But when substrate concentration is high, in other words, all of the enzyme, what matters more than the substrate concentration is the enzyme concentration. The real factor that determines that initial velocity is the amount of the enzyme substrate complex, because in a simple kind of two-step reaction like this, you simply have one substrate reacting with the enzyme to form the enzyme substrate complex, and then the enzyme substrate complex converts the substrate into a product and then releases the free enzyme. And so each of those reactions has its own step and its own rate constant associated with it. So the formation of the enzyme substrate complex, the rate constant for that we call K1. Now the enzyme substrate complex can either go on to form the product, and that if that happens, that rate happens with a constant of K2. But if the enzyme substrate complex gets separated, if it goes back for the reverse of that reaction, then there's a reaction constant for that, K-1. And then sometimes the enzyme can actually reversibly turn the product back into the substrate or back into the enzyme substrate complex, and that happens at a rate of K minus 2. Now at the beginning of the reaction, again, when product concentration is very, very low, we can ignore the reverse reaction here. We don't need to worry about K minus 2. It's basically negligible. And we can also make the assumption that the second step here, the conversion of the substrate into the product from the enzyme substrate complex, is rate limiting. So we assume that K2 is the rate limiting factor. And for that reason, all that really matters for V0 is the concentration of enzyme and substrate complex. So we say that V0 then is proportional to the enzyme substrate complex concentration, and then the rate constant K2. So again, this is kind of a simple model of how enzymes work. And then these two folks, Leonor Michaelis and Michaelis-Menten, worked out a mathematical way of kind of describing how initial velocity of a reaction changes with substrate concentration. And they use a few assumptions. First, we can talk about, again, if all we care about is the enzyme substrate concentration, which again is the assumption we're making for V0 here, then we just need to worry about how is that complex formed and how is it broken down. So again, there's two ways it can be formed. One is the enzyme substrate complex forming from the free enzyme and the free substrate. So that's this reaction here. Or it can be formed by the enzyme converting the product back into the substrate and reforming the enzyme substrate complex. But again, initially we don't need to worry about that because this reaction is so slow, especially with the product concentration being basically 0, that it's not really going to matter. So for the formation of the enzyme substrate complex, we only need to worry about that forward reaction, and its rate is going to be equal to K1 times that enzyme concentration times the substrate concentration. Now, if you have, we'll talk about later about what would happen if you had perhaps 2 substrates, but for now we're just assuming that that's the only thing that matters for the formation of that complex. But again, we want to get this in terms of the enzyme substrate concentration, and so we know that the enzyme is only in 2 forms. It's either free, in other words, there's no enzyme bound, no substrate bound, or it's in the enzyme substrate complex. So that means that the free enzyme concentration is just the difference between the total enzyme concentration and that enzyme substrate complex. In other words, the amount of total enzyme, all the enzyme added together, is equal to the amount of free enzyme plus the amount of enzyme substrate complex. So in order to get this in terms of just the enzyme substrate complex concentration, I just say that this value, the free enzyme concentration, is equal to the total enzyme concentration minus the enzyme substrate concentration. So that is our rate of ES, enzyme substrate formation. And then the way that enzyme substrate gets broken down is either the enzyme substrate complex dissociates back into free enzyme and free substrate, or it gets converted into the product and you have free enzyme and free product. So there are 2 things that affect the rate of ES breakdown. You have the K minus 1, that's turning it back into free enzyme and free substrate, or K2, which is converting it into enzyme plus product. Both of those are going to be dependent on the enzyme substrate concentration. So the total rate is those 2 added together, K minus 1 times the enzyme substrate concentration plus K2 times enzyme substrate concentration. Now, an assumption we have to make here is called the steady state assumption. So the steady state assumption says that the rate of ES formation and ES breakdown are the same. In other words, especially during the first few seconds of the reaction, the enzyme substrate concentration is constant. It doesn't really change. And for that to be true, this value and this value have to be equal to each other, and so we just set them equal to each other, which is what we did down here. Now, again, what we want to do is we want to show that the initial rate reaction, or we know already that the initial rate reaction is a function of enzyme substrate concentration. The problem is, the reason we're doing this is that it's hard to measure the enzyme substrate complex, even though its concentration is constant during the initial reaction. Usually it's hard to directly measure how much of it is actually present in your your test tube or whatever you're doing your reaction in. So what we're trying to do is get this, figure out the reaction rate, the V0, in terms of things we can measure, which include the substrate concentration. So all we're going to do is rearrange this equation and get it in terms of, or get solve for that enzyme substrate concentration. And you guys can kind of do the algebra for this on your own if you want to, but just rearranging it, you get an equation that looks like this, eventually, where it's the total enzyme concentration times the substrate concentration divided by the sum of the substrate concentration and this constant, which is a combination of our three rate constants that we're concerned with. And because they're constants, we can combine them together, and those combined form this number called the Michaelis constant. And again, this Michaelis constant should be a constant for the enzyme, because again, it's just a factor that's determined by the reaction rate constants. And so now we have enzyme substrate concentration in terms of total enzyme concentration, which we know because we set that, and substrate concentration, which we both set when we set up our reaction, and the Km, which again is a constant that we can either calculate or determine for our enzyme. And so now we want to go back and say, okay, what we're really interested in is how does V0 change then with those values we can actually measure. So we said before that V0 equals K2, little k2, times the enzyme substrate concentration, right? So again, that's because we're assuming that that K2 step is the rate limiting, and we're assuming that the enzyme is saturated. So really that's the only factor we have to worry about, is the enzyme substrate concentration. And then we also know that when the reaction is at Vmax, that means that it's at the maximum velocity it can get to. All of our enzyme is in the enzyme substrate complex. That means this value right here, the free enzyme concentration, is basically zero, because there's so much substrate that the enzyme is only found in the enzyme substrate complex. So enzyme substrate complex concentration is equal to the total enzyme concentration. So what that means is we can change this and say V0 is just equal to K2 times the total enzyme concentration. And the reason that's helpful is that then we can say, Vmax equals K2 times the total enzyme concentration. So what that means is we can come over here, because we have K2 times total enzyme concentration in this region, and so we can replace that with Vmax. So now we have V0 equals Vmax times substrate concentration divided by the sum of substrate concentration and Km. So now we're talking about V0 in terms of Vmax, which we can measure, and Km, which we can measure, and substrate concentration, which we can set experimentally. So now we have a way to figure out V0 from values that we can easily come up with. And so this is called the Michaelis-Menten equation. And it's, again, just a mathematical way of figuring out these parameters for any given enzyme. So a couple things show up when we use the Michaelis-Menten equation. First of all, when the substrate concentration is very low, in other words, we're way down here at this part of the curve, basically it means that if substrate concentration is low enough, smaller than Km, what we can say is we can basically ignore it on the bottom part of our equation. So we can say V0 just is equal to Vmax times substrate concentration over Km. And that's what this looks like here. So again, this line basically is linear, because now V0 is just dependent on the substrate concentration directly. In other words, that bottom part, the substrate concentration goes away on the bottom part of that ratio. Meanwhile, when Vmax is high, or I'm sorry, when substrate concentration is high, when we get to this end of the curve, then we can say that substrate concentration is large enough that we can ignore Km or assume it's 0. So then V0 equals Vmax times substrate concentration divided by substrate concentration. And that means that V0 just equals Vmax, because of course these cancel out. So that matches our experiment, because we know that when substrate concentration becomes very high, the initial velocity eventually approaches that Vmax. Another thing comes up though when the substrate concentration is equal to that Km value. So again, V0 equals Vmax times substrate concentration over substrate concentration plus Km. If substrate concentration is equal to Km, then we can just plug Km there wherever substrate concentration is. So it becomes Vmax times Km over Km plus Km. And that is simply 1/2 of Vmax. So what that means is that by definition, another way of defining Km is it's the substrate concentration at which the initial velocity is halfway to its Vmax. And so that's just another way of describing what the Km is. Now, the Michaelis-Menten equation is useful, but sometimes it's helpful and easier to work with equations if they form straight lines. So one way to turn the Michaelis-Menten equation into a straight line is to take the inverse of it, and this is called making a Lineweaver-Burk plot. So 1 over the Michaelis-Menten equation is just 1 over V0 equals substrate concentration plus Km over Vmax times substrate concentration. And what we can then do is say, well, in this case, it's we'll put Km first, and we'll say it's Km over Vmax times 1 over the substrate concentration plus, on the other side, substrate concentration cancels itself out, and you're just left with plus 1 over Vmax. And so the nice thing about this is now you have, or can make, a straight line. So if you graph 1 over V0, and again, we can measure V0 experimentally, and we know 1 over substrate concentration, so just make a plot of that, you should get a straight line. And where Km over Vmax is the slope, so here's the slope of our line, and then our y-intercept, in other words, where x equals 0, 1 over V0 becomes 1 over Vmax. So here's the x-intercept. Now, in reality, of course, you can't have 1 over s equal to 0, but just mathematically, you can say if it were equal to 0, 1 over V0 would be 1 over Vmax. And then same thing, if 1 over substrate concentration, 1 over V0 were 0, that would give you the x-intercept, and for this equation it becomes equal to negative 1 over Km. And so again, these aren't values that are actually going to exist, but just by plotting this line, you can determine these numbers. So then you can say, well, if the x-intercept of this graph is a certain number, we can take the 1 over that and get the Vmax. If the y-intercept, whereas the x-intercept is negative 1 over Km, again, take the inverse and take the negative, and that will give you the actual Km for that enzyme. So the Lineweaver-Burk plot is just a convenient way of getting to those parameters. Sometimes it's also called the double reciprocal plot, because you're taking the inverse of both of those values. And we'll see examples of the Lineweaver-Burk plot more in a minute. Now, the Michaelis-Menten model assumes a few things. It assumes that K2, again, is the rate limiting step. And of course, it also assumes it's just a simple two-step reaction. But in reality, you may have enzymes with multiple steps, and the rate constant, again, should be whatever is the slowest step in that reaction, but sometimes it can be a complex mixture of different reactions. So instead, a more kind of generic form of this equation uses a what's called the turnover number, or what's called kcat. It's just the overall rate of the reaction. It's basically the number of catalyzed reactions per second. And again, for our enzyme reaction, the kcat should just be equal to the Vmax divided by the total enzyme concentration. Because again, you're talking about, you're not really concerned necessarily with what the intermediate steps are. You're just saying the overall reaction rate at that point. Again, whenever you're dealing with this kind of reaction, you can make some assumptions. So if you're, especially when you're starting at the beginning, when substrate concentration is low, much lower than Km, then the initial velocity for a typical enzyme looks like this, where it's dependent on the total enzyme concentration and the substrate concentration, and then times this ratio, that little kcat, the turnover number, over Km, which again is the Michaelis constant. And those values should be constant for any given enzyme. Any given enzyme always should have those same numbers. And you can also use, sometimes this ratio is called the overall rate constant. And so you can use this to kind of compare enzymes. So the larger this number, the kind of more effective that enzyme is. And you can see that for most enzymes, typical rate constant is close to 10 to the 7th, 10 to the 8th, 10 to the 9th per molar per second. And that is usually as high as it can get, because there's an upper limit on how good an enzyme can be, how fast an enzyme can go, or how much it can increase reaction velocity. And it's usually dependent on diffusion, because no matter how fast your enzyme is, the enzyme at least has to wait for the substrate to come in contact with the enzyme. And so that's what's called the diffusion control limit. So the diffusion control limit is just sort of mathematically how fast an enzyme can hypothetically be if it didn't have to wait, or even when it has to wait for the substrate to come in contact. So so what this shows is that especially for these enzymes in particular, that rate constant, that ratio is very close to that hypothetical upper limit. So what that means is that many enzymes have evolved to reach that overall theoretical upper limit for that specificity constant. Now, what do we do though if we have a reaction in which there are two or more substrates? Because so far we've just been talking about reactions where there's just one substrate. And having multiple substrates does affect the reaction. And because of course you can, the substrate concentrations could be different, and they could change at different rates. And you can look and see, and you can do the Michaelis-Menten measurements. You can measure V0 versus substrate concentration, and create Lineweaver-Burke plots and vary the substrate concentration. And you can see how different substrate concentrations affect V0 and determine what type of reaction you're talking about, because there are basically two types of enzymatic reactions in which you have two substrates. One involves forming what's called a ternary complex, and all that means is that part of the reaction mechanism involves a complex that includes the enzyme and both substrates. So a secondary complex just would involve the enzyme and one substrate. The ternary complex is the enzyme plus two substrates. And there's two ways for that to happen. You can have an ordered reaction where the substrates have to bind in a certain order. So in this case, substrate 1 binds first, and then substrate 2 has to bind second, and they have to happen in that order. And then maybe the enzyme produces two products, or maybe it produces one product, doesn't actually matter that much. Or you could have a random order ternary complex, because which it means that these substrates could bind in either order. Either substrate 1 binds first, or substrate 2 binds first. But in any case, they both have to bind. You have to form that ternary complex for the reaction to get to its product. So if you have this kind of reaction where, again, a ternary complex is involved, and you make a line Weaver-Burk plot, meaning you measure V0 for your enzyme versus substrate concentration. And first you do this for varying levels of substrate 1 concentration, but keep substrate 2 concentration constant, you should get a line. So if you do this the first time, you may get a line that looks like this with, these will be our values. So we just find the best fit line through that graph. And then as we increase substrate 2 concentration, we should see that line change. So if you see this situation where the slope of the line changes, meaning that it starts to get lower and lower as you increase the substrate 2 concentration. Again, we do it more, and that line becomes more and more flat. So actually both are changing, both the slope and the y-intercept are changing at the same time. Then that tells you that you are looking at a reaction with 2 substrates that form a ternary complex. The other possibility is that there is no ternary complex formed, which means that you need 2 substrates, but they don't bind the enzyme at the same time. So that would be a reaction that looks like this, where you have your enzyme plus your first substrate. They form the enzyme substrate complex, enzyme substrate 1 complex. The enzyme produces product 1, and so you have a transition state where the enzyme is bound to product 1. Maybe the enzyme itself is in a transition state where it's temporarily has some covalent modification, let's say. And then once product 1 is released, then substrate 2 can bind to now our new temporary enzyme form, and then you have this new enzyme substrate 2 complex that causes product 2 to be formed, and it causes the enzyme to go back to its original conformation. So there's no ternary complex here, which means that these substrate concentrations are kind of independent to each other, but you can still determine that by doing our line Weaver-Burk plot again. But this time, as we increase substrate 2 concentration, what you would see if this was the type of reaction you were looking at is that the slope of the line never changes. So the change in V0, 1 over V0 versus 1 over S, is not affected by substrate 2 concentration. But what it does do is it affects the x-intercept and the y-intercept. So in other words, you might be increasing either Km or Vmax, but you're not increasing the proportion of those two. So this is just one way you can use the Michaelis-Menten equation and use the line Weaver-Burk plot, is to determine if you have 2 substrates, do they form a ternary complex or not. So it's a way of getting at not only the kinetics of an enzyme, but the actual reaction mechanism that it goes through. And then another way you can use the Michaelis-Menten equation is to study inhibitors. So an inhibitor is any molecule that basically prevents the enzyme from doing its job. Usually it slows down the enzyme in some way. And for now, we're just going to talk about reversible inhibition. So reversible inhibition is when your inhibitor molecule, whatever it is, just binds to the enzyme in some way, non-covalently usually, and therefore doesn't have any permanent change to the enzyme. So the inhibitor can be released from the enzyme and stop inhibiting. This would be the opposite of irreversible inhibition, where the enzyme is permanently modified by the inhibitor. So if you have a reversible inhibitor, there are basically 3 types of reversible inhibition, and they all differ by how the inhibitor actually binds to the enzyme, what part of the enzyme it binds to, and where in the reaction mechanism it intervenes. So this over here is called competitive inhibition. And in competitive inhibition, the inhibitor binds to the same active site as the substrate, which means that the inhibitor and the substrate both compete for that active site. So here's our enzyme, and our inhibitor or our substrate can bind to our active site here. And if the inhibitor is bound, the substrate can't bind, and so it prevents the reaction from proceeding. So the inhibitor and the enzyme form a complex, the enzyme inhibitor complex down here. that reaction has its own reaction rate and equilibrium associated with it. So we use this Ki, big Ki, to talk about the equilibrium constant for the formation of the enzyme inhibitor complex. So again, just like any other equilibrium constant, it's just the concentration of the reactants over the concentration of the product. So it's concentration of free enzyme plus concentration of inhibitor over concentration of inhibitor enzyme complex. Then we can use this number alpha to describe kind of the degree of inhibition of our enzyme. And mathematically, it's just 1 plus the inhibitor concentration. So it becomes, obviously, the inhibitor is more effective as its concentration goes up, divided by Ki. So the bigger the Ki, the smaller or the less effective the inhibitor is, because Ki is the dissociation constant between the enzyme and the inhibitor. And it turns out that if you have a competitive inhibitor like this, you can show experimentally that it affects V0 this way. So it's the V0 of this reaction is, again, according to Michaelis-Menten, will be Vmax times substrate concentration over the sum of substrate concentration times Km times alpha. So what it basically means is that if you have a competitive inhibitor present in your reaction, it will make the apparent Km larger. Remember that Km is, we also define it as the substrate concentration at which the reaction is halfway to Vmax. So it means that with your inhibitor, it takes more substrate to get to Vmax. And so if you have a competitive inhibitor and then you test your reaction at different concentrations of inhibitor, and then make a Lineweaver-Burke plot, you will see this. Again, with no inhibitor, by definition, alpha will be 1. So if the inhibitor concentration is 0, alpha becomes 1, and it just disappears from that reaction, or that equation. But as you increase the inhibitor concentration, again, what you're doing is increasing the apparent Km, but you're not increasing the Vmax. So if we go up here, again, this is our Michaelis-Menten equation, the double reciprocal version of it. And so with the inhibitor, the competitive inhibitor, that its alpha shows up here in the slope of our line, but it doesn't affect the y-intercept. So you should see a line with increasing slope with increasing inhibitor concentration, but the x-intercept stays the same. Again, x-intercept is always 1 over Vmax. So if that value isn't changing with inhibitor concentration, but you do see an increase in the slope, and you also see an increase in the x-intercept, because of course if you're seeing an increase in the slope, you must be seeing an increase in the x-intercept, and that tells you that you are dealing with a competitive inhibitor. So again, what you can do here is you can determine what type of inhibitor the molecule is. And the inhibitors, by the way, lots of molecules act as inhibitors for an enzyme. So sometimes the inhibitor could be a molecule that's naturally found in the cell. Sometimes the product itself of an enzyme can act as an inhibitor. We'll talk about examples of that later on. And sometimes inhibitors can be drugs that are applied exogenously. And then another type of inhibitor is called uncompetitive inhibition. And in uncompetitive inhibition, the substrate binds to its active site, and then the inhibitor binds to some other location. So it binds to a spot on the enzyme that's separate from the active site for the substrate, but somehow prevents the enzyme from working. And in fact, by definition, an uncompetitive inhibitor only binds to the enzyme substrate complex. So the inhibitor can only bind if the substrate is already bound. And so in this case, the equilibrium constant for this inhibitor is, this is its reaction. So it's just combining the enzyme substrate complex and the inhibitor. So its equilibrium constant, which we call K prime I, is the enzyme substrate concentration times the inhibitor concentration divided by the complex of all three, enzyme, substrate, plus inhibitor. So still have this term alpha, which is our effective degree of inhibition, and it's 1 plus, again, inhibitor concentration over that K prime I, because remember, that's basically the dissociation constant for the inhibitor, in this case, and the enzyme substrate complex. And then we can show that when that is the type of inhibitor we're dealing with, it's going to show up here. So the initial velocity, V0, is going to be Vmax over substrate concentration plus the sum of Km, and now the product of substrate concentration and alpha prime. So effectively, the apparent, not in this case, the Km is not going to appear different necessarily, but when we take the double reciprocal plot, what we see is that now this alpha prime value shows up over here in our intercept value, but doesn't affect the slope. So this number Km over Vmax is still the same, which means the slope of our line is going to be the same. But as we add more inhibitor, that alpha goes up, which means that both the y-intercept here and the x-intercept are both increasing. So what that means is that both numbers are effectively changing. So if our y-intercept is getting bigger, it means that the Vmax is going to appear to get smaller. And as the x-intercept gets bigger, the Km is going to appear to get smaller. And so that's what an uncompetitive inhibitor does. The apparent Km and Vmax will both decrease as you increase the substrate concentration. So now, again, you can tell from this graph that you're dealing with an uncompetitive inhibitor versus a competitive inhibitor. And there's also something called mixed inhibition, where the inhibitor can bind to the enzyme, either the free enzyme or to the enzyme substrate complex. And in this case, there's basically two ways for the inhibitor to bind. So there's actually two equilibrium constants, one for the inhibitor binding to the free enzyme, one for the inhibitor binding to the enzyme substrate complex, which means there are effectively two alpha values, both an alpha and an alpha prime, and they mean the same thing as they did for the other two types of inhibitors. And in this case, whether or not it increases, it will decrease the Vmax, because if we look at the double reciprocal plot now, it looks like this. So 1 over V0 equals 1 over S times Km over Vmax times alpha. So that means it is going to change the slope. So the slope will increase as the inhibitor increases. And then it's also going to change the intercept, because the alpha prime is going to affect the apparent Vmax and Km. And if we graph that, what you can see is, again, the slope goes up, which means that the apparent Vmax goes down again. So this raises this value, which means the Vmax is going to, effective Vmax will be smaller. And it will simultaneously decrease this number. But that will depend on that ratio from alpha prime to alpha. So depending on which of these interactions is more effective, whether the inhibitor binds better to the free enzyme or binds better to the enzyme substrate complex, will either make the Km go up or down. But again, if you see this type of change where the slope of the line changes and the x and y intercepts are also changing, that tells you that your inhibitor is exhibiting mixed inhibition. And so this just kind of summarizes everything. So again, with no inhibitor, you can just directly measure the Vmax and the Km. For a competitive inhibitor, it won't affect the Vmax, so the Vmax should be the same, either in the presence of inhibitor or not, whereas the Km should appear larger, and it'll be proportional to that alpha value, the parent Km. An uncompetitive inhibitor will make the Vmax look smaller because it will be inversely proportional to that inhibitory factor A alpha prime. And then the Km also will appear smaller to the same degree. And then for mixed inhibitors, again, Vmax still is going to be dependent on alpha prime. Now, the reason that the Vmax only changes or eventually is only dependent on that one type of inhibition is because the Vmax really is dependent on the substrate concentration. So when the substrate concentration is so high that the inhibitor really doesn't even have a chance to bind, it doesn't really matter if it's competitive or uncompetitive. I mean, if it's uncompetitive or mixed. Meanwhile, the Km can change when mixed inhibition, either up or down, depending on how well the inhibitor binds to the free enzyme versus the enzyme substrate complex. So if that alpha value is higher, Km will appear to go up. If the alpha prime value is larger, then Km will appear to go down. All right, so next time we will just talk about some, at least one specific example of an enzyme, and we'll go through the actual mechanism of its reaction.